Do you need to get away? To escape? Is gravity getting you down? I know the feeling. In this video, we'll derive a formula for escape velocity and look at examples in real life and in Kerbal Space Program.
Okay, so here's what we're doing. Derivation of escape velocity. It's a lesson in calculus, particularly improper integrals. So I'll start saying work is force times distance. And this is work defined in mathematics and physics, and also can be interpreted as a change in energy, both potential or kinetic. And I'll talk about those terms as we go along. So what we'll do is we'll think about the work that the rocket needs to do to escape the gravity of a planet, or the sun, or a moon. We'll look at that work as the summation of the force of gravity multiplied times incremental distances summed out through the entire distance that it would have to travel to escape the gravity field. Here, in a derivation of the theoretical escape velocity, you actually have to go an infinite distance to completely escape the gravity of a planet or a primary body. So we'll say from some distance from the primary body, r1, to some infinite distance. Here's the force that needs to be applied to counteract gravity. It's the universal gravitational constant, the mass of the primary body, the mass of the orbiting body, divided by the radial distance squared. That's Newton's universal law of gravitation. That is the force due to gravity. But here I'm keeping this, thinking about it, the force that the rocket actually has to provide multiplied by the distance that it has to travel. So this is a force right here, and this is the distance. And multiplying those two together give incremental amounts of work. This is the integral sign that actually represents an S, a fancy script S for summation, and what we're doing is we're adding together the changing force times incremental amounts of distance. So these are incremental amounts of work summed. We say integrated just means putting it together, putting all of those contributions of the force times distance, the contribution of work on the entire distance from some initial distance r1 from the primary body out to infinity. So this is an improper integral because it has this infinite bound. So m represents the mass of the primary body, little m is the mass of the orbiting body, g is a constant that just really ultimately is about the units that you use for measuring distances and time and mass. Well, evaluating this improper integral, what we could do is say that we'll do a limit as some arbitrary value b goes to infinity of the integration from r1, the initial distance, to r equals that b value. So that'll be a definite integral that we can use Calc 1 principles, the fundamental theorem of calculus, because this is not a difficult function to find an antiderivative for. It's just the power rule. It's just really integrating with respect to r means that we just need to find an antiderivative of 1 over r squared, because the g and the m and the little m, these are all constants. So why don't we write those in front? We could actually take them out of the limit because they're not going to change with b either. But I'll just write it here and say this is from r equal r1 to r equal b. This is just over 1. And then let's write this as r to the minus 2 so that you can see I'm just taking this factor r squared in the denominator, writing it as r to the minus 2 because I can find an antiderivative, a function whose derivative is r to the negative 2, easily by the power rule. So at this point, you find the antiderivative by adding 1 to the negative 2, so it becomes r to the negative 1 over negative 1. That's the power rule. And then I have I'm going to evaluate at these different r values, r equal r1 and r equal b. So we'll plug in the bounds. That's the fundamental theorem of calculus. And then we'll evaluate the limit at the end. So let's write this as negative gm little m over r evaluated at these endpoints. We plug in the upper bound first, subtract, plug in the lower bound, which was r1. Okay, now that's the work done by the rocket escaping gravity, and we now want to just, well, actually up to the point B, to a radial distance B, and then we look at what happens when that B goes to infinity. We take the limit as B goes to infinity, and of course, because that B is in the denominator there, this guy is going to 0, and therefore its limit equals 0, and so the limit is equal positive, because I have, of course, here I have a minus minus, so that becomes a positive, gm little m over r1. So that's the work done by the rocket escaping this infinite gravity field. So, of course, this is a theoretical result. You don't necessarily have to go to infinity to effectively escape the gravity of some primary body. Of course, in real life, once you go far enough from the Earth, you're going to be your path will be the gravity field is the sun will dominate the gravity field, perhaps, or maybe it's the moon, or maybe Mars, depending on the position. Right? I want to say that it's just a really interesting mathematical point to make, that it's simply because of the nature of this force due to gravity, the fact that it has an r squared in the denominator, the nature of the force of gravity, that such a theoretical value even exists. If this had been r to the 1 or anything less than 1 for that power there, then there would have been no theoretical escape velocity. It's essentially what's being demonstrated mathematically is that the gravity field drops off fast enough as you go far away because of that r squared in the denominator, that there is this theoretical real number that is the escape velocity. It is that it's going to represent, well, we haven't got to that yet, but this is the amount of work. There's a real number change in energy required to escape the gravity of the primary body. And now we'll just have to figure out what is the velocity required to get that work done. All right, let me reiterate that this expression that we just got here is work done by the rocket escaping the gravity field of some primary body. This is also representing the change in the potential energy of this rocket, a positive value, as the potential energy increases as the rocket moves further from the primary body. So this represents a change in the potential energy. And now to derive our formula for escape velocity, we'll look at the kinetic energy that provides that change in potential energy. So let's derive a formula for kinetic energy, and then we'll equate them. So for my purpose here, I'll say also a change in kinetic energy is some force times distance. And the force I'll represent as some mass times some acceleration times that distance. And before you get mad about all this work that has to be done, let's quickly replace the acceleration over some interval of time with a change in velocity over some interval of time. So let's just say for the moment v final minus some v initial divided by an interval of time. That's representing my acceleration. And then the distance, what I'll do is I'll just represent that distance as the average velocity over some interval of time. So this will be velocity final plus velocity initial divided by 2 as the average velocity times some increment of time. So this is the distance, and this is the acceleration. Now right away what I want to do as a mathematician, I want to cancel those out, and I'm going to say let's make this equal to 0, this initial velocity 0, so that we're just measuring a change in kinetic energy from a change in velocity from not moving to some final velocity. So this expression for change in kinetic energy has become mass times that final velocity squared. Well, let's write it out one more time. We have the final velocity, another factor for the final velocity, all over 2. So this is this familiar 1/2 mv squared that you might see. Let's call it still the final velocity. That is my kinetic energy, the change in kinetic energy from 0 to some final velocity vf. Well, it's now at this point that we can actually equate the change in kinetic energy, or the total energy provided by the velocity of the rocket, to the potential energy that it needs to increase to escape the gravity field. It's this really important principle in physics of this conservation of energy, as we're basically looking at that kinetic energy that's required to equal the potential energy to leave the gravity field. So let's say that that kinetic energy is at escape velocity. To escape the gravity field of a primary body from a distance r1 from the primary body. So here we can cancel the small m from both sides of this equation representing the mass of the rocket. What I'm doing here is also kind of assuming this sort of instantaneous change in the velocity at an instant where, of course, in practice that couldn't possibly happen. You couldn't instantly change your velocity. You'd have to burn fuel over possibly a long period of time, reducing the mass of the rocket to increase the velocity. So I'm coming up with a theoretical result for an instantaneous escape velocity at a particular altitude. And then we can look at how that plays out in more practical real-life examples. We have this theoretical value that we can see in real-life examples that we're approximating. So I have this expression 1/2 the escape velocity squared has to be gravitational constant, mass of the primary body, over that distance r1. And of course now I'm solving for the escape velocity. So I have escape velocity squared would be 2 times gm over r1, and taking a square root of both sides. Now, of course, it's a plus or minus algebraically. You could even consider both plus and minuses as being kind of valid because you can escape one direction or the other, but really, we're really talking about the speed, the escape speed, and we just say velocity loosely. Technically, the velocity really includes the direction, and so I'm really calculating escape speed, so let's just make that the positive. So we'll say the square root of 2gm over r1. Now I'll just, let's say this. That's basically the result. This is the escape velocity that's required, starting at a distance r1 from the primary body. Now, it didn't really said anything about what direction do you go, definitely away from the primary body, but actually, as velocity increases up to escape velocity within the gravity field of the primary mass will continue to bend the trajectory of the orbiting body. At the instant the velocity hits the theoretical escape velocity, the path away from the primary body would actually be a parabola, and not a straight line path away from the primary body, and thus still the primary body is influencing the path of the rocket or satellite, even as it travels forever away from the primary body. Of course, in practice, it's essentially impossible to hit precisely this theoretical value of the escape velocity, and in practice, there's a point where the object traveling at escape velocity has reached far enough away from the primary body that the gravity field of other objects like the sun or another planet or moon begins to dominate and bend the trajectory. So when the object is moving at less than escape velocity, its orbit is elliptical, and the eccentricity is less than 1. However, once escape velocity is exceeded, the orbit becomes hyperbolic. The eccentricity will be greater than 1, and the trajectory is no longer bound to the primary body. Now, if you actually were initially in a circular orbit, let's write the velocity for, orbital speed for a circular orbit is a similar expression. I've derived this in other videos, so I'll just write it here. This is orbital speed in a circular orbit. So it's pretty neat to look at how very closely these two expressions are, and actually we can relate them. If I start with escape velocity at radius r1, I can just factor out that square root of 2. This means escape velocity is about 1.41 times orbital speed at a particular altitude. This is meaning that the escape velocity is approximately a 41% increase over the orbital speed at a given altitude. So let's look at an example. The mass of Kerbin is 5.29 times 10 to the 22 kilograms, and its radius is 600 kilometers. What's the escape velocity at an altitude of 100 kilometers? Escape velocity is this 2 times gm over the orbital radius. So the square root of 2 times gravitational constant, 6.67 times 10 to the negative 11, the same value used in real life physics as in Kerbal Space Program, and the mass of the planet, 5.29 times 10 to the 22. Here we're looking at a planet radius of 600 kilometers, so we need to write this in meters. So we'll say 600,000 meters plus an altitude of 100,000 meters, and let's put that in a calculator. We'll just add those together. That's 700,000. It's about 3175 meters per second. That's escape velocity, but what we'll usually be looking at is that we've already got the orbital speed at, let's say, 100 kilometer altitude, and we just need to increase the speed to escape velocity. So velocity for a circular orbit at that altitude, this is gm over r. The only difference here is I don't have the square root of 2. I need the distance in meters. So putting that in the calculator, you're going to get about 2245 meters per second. Of course, I could have just done this first, find the orbital speed, and then just multiply by the square root of 2. So note that if you just took the orbital speed for that altitude and multiplied by the square root of 2, you'll get that 3175 meters per second. And in practice, it's about the delta V that you need to increase the speed to escape. So what is the delta V? The change in velocity would be the final velocity we need theoretically to escape from the planet minus the current speed for orbital speed for that altitude. This is about 930 meters per second additional velocity. Now, actually, even in Kerbal Space Program, you don't actually need that theoretical value because, just like in real life, there is this idea of a sphere of influence around the planet that once you get far enough, you'll be in the gravity field of the Sun or the Moon or Mars or Duna. And so those other bodies will be the primary influence on the gravity field. So in practice, less than 930 is sufficient to escape the sphere of influence of Kerbin. So I did check this in Kerbal Space Program and launched a rocket to an altitude of 100 kilometers above Kerbin, and at a speed of about 2245, you'll see in the clip I'm about to show that I checked a delta V of 930 meters per second, and that was definitely going to escape the gravity of Kerbin. And I also tried 900, and that wasn't enough. So it was somewhere between 900 and the theoretical value of 930. You didn't really actually have to go 930 to actually escape the sphere of influence of Kerbin. It might have been like 905 or 910 that was sufficient. But 930 was the actual theoretical value to completely escape the gravity field. So that's what I ended up using, and this is what it looked like. Alright, so at this point we've reached space, and we're just going to coast up to that highest altitude, the apoapsis, to then once again burn, to circularize, to stay in orbit. So we're now at orbital speed, and we'll prepare for another burn for escape velocity. Approximately 100-kilometer altitude circular orbit. Now I'm adding a maneuver to increase the speed by 930 meters per second. And here's the point in the trajectory where we will escape Kerbin's gravity. Now I'll add another maneuver at 900 meters per second, delta V, but you'll see that this is not enough to escape the sphere of influence of Kerbin. We come back to orbit Kerbin in an elliptical orbit. So now I just set the delta V back to 930 meters per second and fire the thrusters. We need to increase the velocity up to about 3175 meters per second for escape velocity at this altitude. And that's it. We're now on an escape trajectory, leaving the gravity of Kerbin. And now we're in a heliocentric orbit, an orbit about the Sun, with orbital speed measured relative to the Sun. So let's look at example 2. The Earth's radius is approximately 6,380 kilometers, and its mass is approximately 5.97 times 10 to the 24 kilograms. We'll compute the escape velocity at an altitude of 300 kilometers. So again, right back to the same formula that we had previously, with the same universal gravitational constant for g, 6.67 times 10 to the minus 11. Now I'm doing the same calculation I just did with Kerbal Space Program, but substituting now in the mass of the Earth. This is the radius of the Earth in meters, so I'm converting that 6,380 kilometers into meters, and a 300 kilometer altitude into the distance in meters, and I come up with 10,919 meters per second. Typing that in the calculator. Now that I've calculated escape velocity at an altitude of 300 kilometers above the Earth, I'll make the point that escape velocity is different not only for different planets, but at different altitudes above a planet, or moon, or other primary mass. For example, escape velocity at 100 kilometers above Kerbin was about 3,175 meters per second, whereas at a 100 kilometer altitude above Earth, escape velocity is about 11,000 meters per second. And you can see also here in this example at 300 kilometers above Earth that escape velocity is a little lower at the higher altitude. This is a graph of escape velocity as a function of the radial distance from the center of Earth. At the top here I have, of course, the universal gravitational constant. This is the mass of the Earth. What I have here in blue is this region that is commonly considered low Earth orbit from about 160 kilometer altitude to about a 1,000 kilometer altitude above the surface of the Earth. So I'm using 6,380 kilometers as the radius of the Earth, which is an approximation. It's not perfectly spherical, but it's one simplification that we can make here. Of course, this is the formula that I've been using for escape velocity. Here I'm using x as the radial distance from the center of the Earth. So the escape velocity required to escape Earth's gravity is this green curve with greater and greater distances from the center of the Earth. You can see the escape velocity clearly getting lower as the altitude increases. The point that I've plotted right here is actually at the surface of the Earth. At the actual surface of the Earth, escape velocity would be 11,172 meters per second. And the point that I have right here is the one that we just previously calculated at an altitude of 300 kilometers. You can see my altitude showing up right here. So I can just vary this point through this range that is low Earth orbit, looking at different escape velocities within that interval. I'm also using Desmos to calculate the speed in kilometers per hour, in miles per hour, and in feet per second. Just out of curiosity, I also included the moon's distance and what the moon's orbital speed is roughly in meters per second at its distance from Earth, and what the escape velocity would be there. So it would require an increase of about 400 meters per second for the moon to escape the gravity of the Earth. That point's way out here. Anyway, the point is escape velocity is not changing that much on the interval representing distances at low Earth orbit. The values really are ranging between about 11 kilometers per second to about 10.4 kilometers per second, depending on the altitude. In that previous example, I calculated escape velocity at Earth at 300 kilometers altitude, and I'm now going to compare that value with two real-life examples, the Mars 2020 Perseverance mission in July of 2020 and the Apollo 11 mission to the Moon in July of 1969. So what I've pulled up here is a stream from the everyday astronaut Tim Dodd, which I really enjoy very much, learn a lot from him. And what he's doing here is streaming this Mars 2020 mission back on July 30 of 2020. And this is right near the point when the spacecraft is finally sent on its way to Mars. So we can see the speed right here as it's gaining, and it's only at 160 kilometers, but you'll see by the time it ends, it's like an 8-minute burn. And yeah, I can also notice just barely here how the apogee, the farthest distance, is climbing and climbing and climbing. And so we're looking for that to reach past 10.9 or 10,000 meters per second, something larger than 11,000 meters per second, to be on the way to Mars. And yeah, we'll see that altitude increase up to, I think it was something like 500 kilometers at the point when it finally was on its way to Mars. So this is the trans-Mars injection burn that ends at about 52 minutes and 50 seconds into the flight. And we're at 48 minutes right now, so I can see this is going to take a little longer. So we might just jump ahead a little bit. Yeah, so there it's at 10,600, coming up on what I know is the escape velocity roughly at an altitude of 300 kilometers. This is a little bit higher than that, but yeah, you see we're going to go past that 10,900 meters per second needed at an altitude of 300 kilometers. And it's going to cut off at about 52 minutes 50 seconds, so it's nearly there. There we go. It's pretty much past, and it's cut off the telemetry for the earthbound trajectory, so it's now on its way to Mars at this point. So it has to burn a little bit further than just enough to escape the Earth's gravity. It has to actually raise its farthest distance from the sun, because it's now going to be in a sun-centric orbit. It needs to extend that orbit a little bit further out to Mars. So that's why it's going past the escape velocity. This will be a topic for another video, this hyperbolic excess velocity. It's just fascinating to say that. So there it is now on a hyperbolic orbit to Mars. Just about to end. There it goes. So he's hoping that it's on its way, and we all know now that it landed successfully and was a very impressive mission. So far, fantastic. Yeah, and I notice now that the speed is actually dropping, and it will continue to drop as it's on its way to Mars. Okay, so the next thing that I'll look at is this website, apolloinrealtime.org/11. So this is a transcript of the Apollo 11 mission to reach the moon, and this was July 16, 1969. We can see mission status here: on the way, traveling to the moon, in the command module. Currently at 32,000 feet per second. That's about 36,000 kilometers per hour, about 22,000 miles per hour. Imagine Mach 29. But this is not fast enough right now to reach to the moon. This is the orbital speed that they're in before they get this call for the translunar injection. So your go for TLI was this, wonderful news that they're cleared, everything checks out, they're ready to ignite the upper stage, the Saturn 4B, again to send them on their way to the moon, to increase their speed up to nearly escape velocity, but not quite. So this is my point right here, is just comparing, for example, with the Mars 2020 mission, how that was beyond escape velocity and reached actually to Mars. And this will be less than escape velocity. And is enough to reach the moon, but if they needed to, they could decide not to go into lunar orbit, and they would just fall back to the Earth because they're on an elliptical orbit, because they haven't reached fully to escape velocity. So because this is not written here in meters per second, I did the conversion so we can compare. So escape velocity again was like 10,919 meters per second. So I convert that into miles per hour and kilometers per hour and feet per second. So we're looking for something in the range of 24,000 miles per hour, but actually just short of that, just less than 35,000 feet per second. So as to not escape completely the gravity of Earth and just going to the moon. So let's listen in and see what speed they actually reach at when the Saturn 4B cuts off and they're on their way.
Apollo 11, this is Houston, through Carnarvon, radio check, over. Through Carnarvon, Apollo 11, loud and clear. Roger, you're coming in very loud and very clear here. Out. Guidance flight. Go flight. Go, I'll go for TLI. Stand on flight. GNC flight. Flight GNC. Go, I'll go for TLI. We're go flight. Decom. We're go flight. Surgeon, we're go flight. Fido, we're go flight. Petro, go flight. Guys, go flight. Thank you.
Going through all the checks.
That works flight, how about you? We're go flight. Great. Okay, Captain. Apollo 11, this is Houston. You are go for TLI, over. Apollo 11, thank you. Roger out.
All right, it takes a few minutes before they actually light the engines, so let's jump to that moment. Mission milestone, translunar injection. You'll hear them call out injection, and then they're starting the burn.
Ignition. We have ignition flight. We're go. Thrust is go. We confirm ignition and the thrust is go. Guys, initiate flight. Auto radar confirmed ignition. We're go.
So I don't want to cover up that beautiful image there.
Good.
But remember, what we're looking for is something
26,000 feet per second.
close to 35, but less than that. Escape velocity is 35,000 feet per second. They're not going to quite reach that. They'll be close to that, but less than that, so that they're still in a bound orbit around Earth. So they're still going to fall back to Earth unless they go into lunar orbit, which of course they did.
1 minute. Trajectory and guidance looks good, and we're saved as stated.
Remember, we're looking to see how close they get to 35,814 feet per second, which would be the theoretical escape velocity at an altitude of 300 kilometers. The engine burn here takes about 6 minutes, and I'm watching both the current velocity increase and the distance from Earth increase.
Velocity 32,000 feet per second. Altitude 130 miles.
And you notice the altitude gets up to about 280 kilometers during the engine burn, but their initial orbit is not even perfectly circular. It even begins to drop as they continue to gain speed. Ultimately, from this recording, I see the speed max out at right around 35,400 feet per second. So yes, they did stay within that escape speed number that I had calculated. It got really, really close, but still was less. So this indicates they're on a free return trajectory, meaning their orbit is still elliptical, and without any additional orbital maneuvers later, they would return to low Earth orbit.
Apollo 11, this is Houston. We show cutoff, and we copy the numbers on now 62. Houston, Apollo 11 inside and gave us a magnificent ride. All right, you're 11. We'll pass that on, and it certainly looks like you're well on your way now.
So just short of the escape velocity, very close, but less than that, just enough to get to the moon.
That's right, it was all a good ride.
Well, I could keep going and listening. Beautiful, fascinating. We'll come back to this for another topic. All right, well, let's go back and check on that satellite that I sent out on that escape mission.
This is Apollo Control at 3 hours into the mission. Velocity now 31,214 feet per second.
Everything looks nominal. Okay, that's the end of the video. I hope it's been interesting and that you learned some things about escape velocity and some calculus too, and thank you for watching. Please hit like and subscribe for more, and check out the Kerbal Math and Physics Lab workbook that I wrote, and more videos like this one at sites.google.com/KSPmath.